Aristarchus of Samos. He measured the size of the moon in 230 BC using little more than his eyes to look at the sky. If you want to try this yourself, you won't need much. Just a clock, Google, and to go outside during a lunar eclipse. These happen once or twice a year. Check the linked video below to see how he originally knew the size of the globe in 230 BC. The key to Aristarchus's method is shadows. Lunar eclipses occur when the moon is inside the shadow of the Earth, in an area called the umbra. This dark section is a slight cone shape, because the edges of the shadows are blurry. You can check this yourself by holding up a ball at noon on a sunny day and looking closely at the shadow that it casts. Here on screen we have a picture of the other type of eclipse. This is a picture of the moon's position during a solar eclipse, where the moon blocks the sun. During a solar eclipse, the size of the shadow on the Earth is relatively pretty small. Here is a picture of the shadow's path on the Earth during the 2024 North American eclipse, as an example. The moon must be quite large because it's very far away, and looks the same size as the sun in the sky. Because the shadow is very small and doesn't cover much of the Earth, we make the assumption that the moon is larger than the shadow that it casts. Since the moon and the shadow form most of a cone, or triangle, we can say that the shadow reduces in width by roughly the same width as the moon for every distance d, which is the orbital distance of the moon. Now, let's flip the picture back to the lunar eclipse. In this case, the Earth also has a shadow. This shadow is larger, but it is the same shape and angle as the moon's shadow, so the two shadows are similar triangles. This means that they have the same angle. Because the shadows are similar triangles, the width of the shadow of the Earth also decreases by one moon's width in the same distance d. The part of the shadow where the moon will move through during a lunar eclipse must then be the length of the Earth's diameter minus the moon's diameter. Now we can look at the sky and measure it in real life. What we need to do is measure how many moons fit across the Earth's shadow. The moon moves the same distance as its width, roughly every hour. So if we measure how many hours the moon is in total darkness during a lunar eclipse, this is how many moons will fill it. If you take the measurement like Aristarchus did, you will see that the moon is in darkness for roughly 2.5 hours. Therefore, the shadow of the Earth is 2.5 moons wide. Earlier, we worked out that the shadow at this point is also the size of the Earth's diameter minus one moon's diameter. Equating the two expressions, and substituting in the diameter of the Earth, we can easily rearrange the algebra to find that the diameter of the moon is roughly 3,641 kilometers. If we divide the value we found by the actual value times 100, this will give us an error as a percentage. Our calculation was only 5% bigger than the actual value, and we didn't even have to go to the moon with a tape measure. On screen, I've put an outline of the full method in case you want to try this experiment yourself without skipping through the video. Here are also a few of the upcoming total lunar eclipses. It might vary depending on where you are on the globe, but you can find these dates easily online. If you're still watching at this point, thank you for watching, and if you're currently looking for help with anything maths related, I offer maths tutoring online. Please check the details in the description to get in touch with me.